due to the delay, you might have heard that still. So this is just going to be a quick stream to check that there are no major errors in the multiplication system. So how I'm going to do that, I'm going to, so I've hardwired this side to go through here. And then I've just set this side generically to all on. What this means is that every one of these gates and the bit shifters over here should be open, allowing essentially whatever number I input over here to get maximally bit shifted and summed, returning out here. So if I put in a 1 on this side, it's the same as going 1 times 16. Well, it's the same as going 1 times whatever the maximum number, a 16-bit number is, which I've forgotten. It's like 12,000 or something. And what that means is that essentially all of these should be on this side, right? And say I take that 1 off and I put two times on it. That is the same as bit shifting all of these by 1. So all of these should be on except the bottom one, and so on to the top. That I think is going to be the most efficient way of testing it. Also off stream I added NOT gates here because this needs to be inverted. And I cleaned up this bit of it. But yes, right now you can see maximum number times 1 is equal to maximum number. Oh yeah, let's check it here, that's what I put that there for. So the bottom one should go out. And it does. It's actually not too slow, this multiplication. It's not too slow at all. Then actually it will slow down dramatically when because binary adder is very slow when it has to carry the 1, because it's got essentially it turns into an in series process rather than a parallel one. But for this, there's no overlapping ones, so it's fine. It hasn't got a round up, not round up, whatever the hell the math term is for that. Oh no, that's broken. It might be an insta-wire fault. So it's this guy here. Those are all confirmed to be working. I should start from here. So it's this one that's not on. Ah, broken there. So I think cycling like this does test every pathway. Essentially, what I want to be able to do is identify all of those little faults like that one I just fixed. I'm trying to think if this particular method I've devised will do that, and I believe it will. Um, it really ought to. It's only running on like 3 seconds of delay. It's about an order of magnitude faster than I thought it would be. So essentially, let's try. I'm going to try artificially breaking some to test the idea that this should test all of them. Mm-hmm. That break shouldn't affect this at all. So it should send one signal through and then one signal out. It only has one output, so this turns on. So when that one turns on, that one is on, so there's no overlap there. Then with that one, that one. Yes, what I just did should have changed for all of these different lines to see if they're all connected correctly. Which I know it doesn't seem like it would have done, but I break this line here. There we are. Yeah, which one did I break? It was over here. So that verifies that the lines are all connected. Now, they know the binary adder works and that the I am going to say that this now functions. I think I'm going to pass this off as functional. Um, so this is basically the binary multiplication unit. Um, I guess I'll just do a quick walkthrough for people who haven't seen it before. So you've got see the whole computer runs on 16-bit system. So this is the 16-bit input bus. This is the address bus and controller here, and then this is the state sensor. So essentially, what it does is it listens for when the address bus gets turned on. This switches that on, which then, well, the first signal that comes through this line from the CPU will get sent into this memory buffer here, and then allowed to passively propagate through while this side is switched off. Now that's handled by this state sensor here. So once this memory buffer has been filled up, this state sensor here switches to the next state, which means that when the next signal is received, the next 16-bit number comes down the memory bus. It gets sent this way and switches. Well, this is the bit shifter. So essentially, what I've got is I've got a system that bit shifts the one number by the powers of two of the other number. So all of the ones in the second number correspond to a order of bit shifting in the first number, and that's what this does here. So you have the so at this end, this one here bit shifts the first number by 16 bits. So if the first number is 1, then it gets shifted up to 256 or whatever it is, over 2 to the power of 16. It's not 256, is it? But whatever it is, gets bit shifted to that. I'm a terrible computer scientist, but also and everything else would get bit shifted to a number that's larger than a 16-bit number. So I have not included the bit shifters for the other ones, right? Because they just basically they overflow. Then this is the 15-bit bit shifter that can bit shift 2-bit numbers. Then this is the 14-bit, this is the 13-bit, and so on until you get to the identity, which is the 0-bit bit shifter. So it's just the equivalent to multiplying by 1, right? And then, of course, but once you've bit shifted into all of these different numbers, you have to recombine them into one number, which means doing a summation, right? So we've got 16-bit, 16-bit numbers. Well, 16 pseudo 16-bit numbers because most of them, obviously, like this one at the end here. This one at the end here is only has one meaningful bit, right? The rest of them are all phantom bits because it's been bit shifted at the top and so on. But either way, treat them like 16-bit numbers. So you've got 16 16-bit numbers to sum over. Now, the quickest way that I know of to do that is to use the binary adders in this triangle formation. So essentially put it into parallel as much as possible. So whilst this one's summing, this one's also summing, and this one's also summing simultaneously, so it's not too slow. And that way the each signal only has to go through 4 binary adders. as opposed to having to go through 8. Like if you had it summed in a line, so some summation from this one then went to this one, summed with that 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 one, some. I think that actually I think that would actually be 16. So it would be 16 times. Well, it would be 4 times slower if I did that, rather than having it in this parallel flow triangle shape. And then, of course, very simply, it just gets fed back round to the start, where it gets put into this output memory buffer. And when the stator gets toggled again, this will then propagate the result back towards the CPU. Well, it is the CPU, so back towards the CPU control circuit. And this is a single multiplication logic operator. At least a math operator, isn't it? But so next I need to figure, because I'm doing all of the mathematical operations, I need to figure out how to do division, and I need to figure out how to do two's complement, subtraction, or whatever it is. And I'm probably gonna have to look this up because I'm just not that smart. But also this here, this is the binary comparison. So this is greater than or less than or equal to. Versus redstone multiplication, which is absolutely massive. Oh, that's the other thing I need to figure out what I'm doing with the trunk loaders for all of these. I should probably actually set up the trunk loader for this before I well, I'm gonna have to redesign it anyway when I plug it into the CPU, so it doesn't really matter. The trunk loading, that is, because obviously this is so the CPU. So obviously the computer is so large that like my computer, well, my character can't render the whole thing at any given time. Therefore, I need to use command blocks to force trunk load. Um, which means I need to set up a bunch of command blocks for logical operators. So when this address bus gets switched on, for example, it needs to switch on a command block that will force trunk load this whole region. And there's actually a bunch of subtlety with that because of these insta wires. These insta wires break if they get caught in loading or unloading trunks. If they get caught toggling in loading or unloading trunks. So gotta be careful about that one. When these things break, it's absolute nightmare. The whole, imagine every one of these is sort of broken and out of sync. You just have to redo the whole thing. But yes, because it's going to be changing orientation or whatever, I'll figure that out when I've copy pasted this over to the CPU. And that's the other thing, it's going to need timing circuits and things like that. But oh boy, I'm tired. Oh, it's only Saturday morning. Oh, but I think because I've reached a natural conclusion there, I'll finish for now and think about the division and subtraction. Then I also need to think about decimal numbers and things like that. I mean, I guess I'd say floating point, but I think it's going to be fixed point. Save a lot of command function space, but operator code space rather. But yeah, that'll be all for me. So I'm gonna need to do some work. Right.